Hello, I am going to be working in problem 6.1 of the book. It can be found in page 292. So let's get started. It's a 2 to the 3 factorial design. We already have our data, which was given to us by the book, and also the table of signs. Now, for running Gates algorithm, we must make a sum because Gates algorithm requires for your data to be in 1. So we have a sum. And for Gates, we must have as many columns as we have factors. So 3 columns for 3 factors. And this would be go like this. This one plus this one. This one plus this one is equal to this. This one plus this one. And this one plus this one equal to this. This one will be this minus this. This minus this. This minus this. And this minus this. So now we just grab our whole column and move it. I'm going to erase this, and I'm going to change the color of this column because these are our contrasts. These are going to help us. So the next part is to calculate the effects. So effects. This is the formula to calculate them is the contrast over n, which in this case is 3 because we replicated the experiment 3 times, times 2 to the k, which k is 3 because we have 3 factors, over 2. We run it. So which ones appear to be big? I would say B, C, and AC, but we will have to check that one with an ANOVA table. So ANOVA, sum of squares, degrees of freedom, MSE, Fisher. This is A, B, AB, C, AC, BC, ABC. Sum of squares. The formula for the sum of squares from the contrast is the contrast squared over n, which is 3, so we'll erase it, times 2 to the k, 2 to the 3. This one, error, and total. The way to calculate total is the way we have been doing it the entire semester. The sum of squares of the data minus the total sum squared over 24, well, big N, which in this case is 24 because we have 24 data. This one, the error is minus the sum of all these degrees of freedom. Each one of these get 1. The error has 23 degrees of freedom, and the error gets 16 degrees of freedom. 23 minus 7. The MSE is equal to this one over this one. You can run that one for the entire thing. And Fisher is equal to the MSE over the MSE of the error. I am going to anchor that one for being able to move them. There it is. For the error. So now we need the tables to compare it. and this can be done in Excel by the formula fimp. We want a probability of 5%, which is 0.05. 1 degree of freedom for each one of these, and 16 degrees of freedom, sorry, for the error. So it is 4.94. So I'm going to color the ones that are significant. This one, this one, and this one, which is actually exactly the ones that I said would be significant. Well, the effect said. So it is confirmed. So now that we know that we just care about B, C, and AC, we can just run a linear model with matrices to know what are our parameters. We do this with matrices. We place the data, and as you can see, we only have B, C, and AC. The formula would be X transpose. To forgetting it, we first X transpose times X, then we inverted the X transpose times Y, and then we multiply these last two, and that would give us our parameters, which are these ones. Now that would give us some expected values, and with that we can make a residual table. So our residual table would be this one minus this one, and I am going to anchor this one because if not, it's going to move. There it is. Now I'm going to anchor this one. 1, 2, 3. It's okay. It's okay. Now I'm going to anchor this one. So now that we have our residual table, we can just plot it and see if there is any problem with our residuals. So now that we have this, we need a random order for plotting the residuals, and I'm gonna get this one with a program in internet in this webpage random.org, and it basically randomizes. This is the order, and this is the number cell, or the cell that I am going to graph first, and I'll graph this one by hand, and I'll give it to you in a second. So as there was no obvious pattern found in the residual table, we can continue with doing the residual plots. These are done by taking the averages, where B is minus and B is plus, and just graphing it. And here we have the residual plot for the interaction plot for B, the interaction plot for C, and the interaction plot for AC. So based on those factors, I would recommend, just looking at B, I would recommend for B plus and C plus, because we can want to maximize the hours that the tool lasts. But looking at the interaction, when we have A minus C plus, we can see that it is in accordance. So that would be my recommended values: B plus, C plus, A minus.